Okay, so the next thing we want to talk about here is simply a notation, a description. So one of the things I've got is I've got a vector A, okay, and I want to know what the length of that vector is. What is its length? Okay, what's its length? Well, obviously, we use the Pythagorean theorem. We take the x component, square it, sum that with the y component squared, take the square root of that, gives us the length. But what notation do we use for that? So the notation that we use for length is going to be the absolute value of the vector. So when we talk about or mention the absolute value of a vector, that refers to its length. Dot product, in general, what we want to do, we'll take a vector that looks like this, okay, and then so that'll be my first vector. Then I'll put my second vector like this, okay, and that, one of the things I can do, that's got an angle between those two vectors, and what I can do is I can project that down such that that's a 90-degree angle. So this is this is vector A, and this is vector B, and this bit here is the projection of B on vector A. Okay, so it's basically what I'm going to do is I'm going to take the length of B and I'm going to multiply times the cosine of theta here, and that will give me the projection of B on A. Okay, and so what we're going to do is we're going to take the projection of B on A, which is going to be a length, it's going to have a length, and then I multiply that by A itself. Okay, so my dot product of vector A dotted into vector B is going to be the absolute value of A times the absolute value of B times cosine of theta. Alright, so that's how it looks geometrically. Now how does that work numerically? How would we be able to do this numerically? Well, A is going to have two components. It's going to have, and what we'll do is we'll use A1, okay, and A2 as the two components. Vector B will have components B1 and B2. This is just different notation for X and Y, okay? And then the dot product of A dotted into B, and again we want to use those vector bars, that's going to be equal to the sum. It's going to be the sum of A1 times B1 plus A2 times B2. Okay, so it's a very, very simple mathematical thing. We basically take A1 times B1, A2 times B2, add them together, I get my scalar value for my dot product. What's also very powerful about this is that I can, using the dot product, I can turn around and compute what this cosine theta is. For example, if I do the cosine theta, taking this and reorganizing, okay, so A dotted into B divided by the absolute value of A times the absolute value of B, that's going to be equal to the cosine of theta. And I can turn around and do the inverse cosine and come up with the angle of theta here. This is really, really significant, okay? What if I have two vectors like that and like that, such that they are perpendicular to one another? It's a 90-degree angle. The cosine of theta for a 90-degree angle is 0. So that if I have two vectors where their dot product is 0, that tells me that those two vectors are perpendicular to one another. This is really, really important when we're dealing with multidimensional spaces. It's pretty obvious that I've got two vectors here, or say maybe I have another vector that comes out here, so I've got an x, y, and a z, and they're all perpendicular to one another, and that's all wonderful and great, and we can see that, we can visualize that, but we can't do that visualization so well in 4 space or 5 space or higher dimensions. So what we do is we use the dot product of the different components of those multiple dimensions, and if the dot product is 0, then the various vectors are orthogonal or perpendicular to each other. So that's how we do it. Okay, let's get back to our original set of position vectors. We had position vector 1, which was equal to 3 and 4, and position vector 2, which was -1 and 2. So the question here is, what is going to be the dot product of P1 and P2? So I take P1, dot it into P2. What's that going to look like? Well, what we do is we take the sum of the product of the various components. So 3 times -1 plus 4 times 2. Well, 3 times, that's -3. That's 8. 8 minus 3 is equal to 5. 5 is the value of my dot product of these two vectors. Obviously, they're not perpendicular, totally perpendicular to one another. There's another vector operation called the cross product, and it's shown as P1 cross P2. Okay, P1 cross P2. This actually does not create a scalar value. This creates another vector. This is used in angular momentum and orbital analysis, but we're not going to mess with that right now. We're not going to mess with that right now. So on we go.